I'll switch to my share screen.
Okay.
And I'm going to begin with some artistic contribution. Nancy Hocking wrote to us.
All right.
And this is what she wrote, and you'll see she's an artist, and she has some very beautiful drawings. Let me put the slideshow on.
Hocking and Young.
Yes, that's the Hocking. So
Yeah.
she writes, the glass top table you showed, you remember I showed a table,
Right.
a not table, glass table a while back. At the start of your lecture is an elegant piece. My compliments to the artist. I'm very glad to join such good company. I've been playing around with the knot table as well. I make knots from copper wire and deform them, continuously of course, until the beauty of the knot reveals itself. Then I draw them. My father, J.G. Hocking, was a topologist. It was a while ago. He would have been 100 this year. In the 1960s, he and Gail Young wrote a topology textbook that has had a long shelf life. And I imagine that all of us are familiar with the textbook by Hocking and Young.
Yeah.
Dover Publications reprinted it in 1988, which is an honor, I am told. One of my early memories is of him delightedly explaining the Mobius band and the Klein bottle to me. This is one of her paintings entitled Six Knots from the First Seven Orders of Knottedness. And as you see, she remarks about the difficulty of counting crossings when you have a normal three-dimensional view. Sometimes you have multiple crossings, as you do in looking at the middle one on the top, and so on. But there's a puzzle for you. Locate these knots on the usual knot table. But I really appreciate the beauty of the drawings themselves. They're quite wonderful. I think we could learn something from that for our own sketches.
Yeah, beautiful.
This is another drawing of Scott Carter's Two Twist Spun Trefoil. These are sections of four-dimensional surface in 4 dimensions. And she further remarked, upon my asking her about it, the Alexander Horn sphere from the book Topology by Hocking and Young. My uncle painted a colorful version of this beast. The painting was one of my early memories. It hung in our living room forever. I believe he drew this illustration as well. One of my older siblings remembers my dad and my uncle discussing it before the book went to print. I have always wondered what the source was for this very interesting and beautiful drawing of the Alexander Horn sphere that is in the book by Hocking and Young. So now we know more about it. I wonder if everyone in the group has seen this drawing. This drawing seems to me to be something from my childhood as well, but the childhood probably was teenage years. Okay. Perhaps if Nancy is present, she has a further comment. I guess she's not present today. Let me see. I had some old comments from previous talking. Let me get to that if I can find it. We did mention this. I'll mention it again in case you want to take down the URL. Nice program for doing Celtic knotwork at this site. And when you click on a crossing, it smooths it one way, and you click again and it smooths it the other way. So you can go from this basic ground for making patterns to nice Celtic knots like this. Okay. And then we were talking about the Temperley-Lieb algebra and how one can start with a connection structure and arrive at a product in the Temperley-Lieb algebra in basically canonical form by drawing the diagram, the connection diagram in fully rectilinear fashion like this, and then making note of connections like these in the columns. And when you do that, you get a rewrite of the element in there's a sketch. You get a rewrite of the element in terms of elements in the Temperley-Lieb algebra. And this product is, in fact, the normal form that Jones uses in his paper Index for Subfactors. I should put the reference in here. I will in the slideshow, I'll put the reference. But Jones was not using connection structures. He discovered this kind of normal form on the basis of the algebraic relations. And we talked about that. But I had a couple of more comments about it, if I can find them. Let me see. Here's an example, and then I'll point to the next example. In this example, we know from the beginning, since it was made, this example here, it was made by cutting this piece in half and rewriting it in the opposite order. So we know that when we close this up, it's the same as closing this up, and there will be two loops. So if you were to make the careful drawing and count, you would find two loops. But the question is, how would you find out how many loops there are by algebraic work on the Temperley-Lieb algebra itself? And that count is related to the trace in the Temperley-Lieb algebra. So let me remind you about that in case you wanted to think about the trace. We're going to define a trace on the Temperley-Lieb algebra into z of delta, where delta is the loop value. I don't have to write it as minus a squared minus a to the minus 2 unless I want to. And then I'll define the trace to be equal to, I'll define the trace in this diagrammatic context to be delta to the norm of x bar, where the norm of x bar is the number of loops in the closure. So for example, here is the closure of this Temperley-Lieb element, U1 in T3. And when you close it, you get two loops. So the trace is delta squared. Now, it's easy to see that this looks like a trace. That is, trace of a product is equal to the trace of the reverse product, because after all, when you close it, AB bar is the same as BA bar when you close it. So that means that you can identify certain traces. And also, if you have a descending sequence like this, A5, 4, 3, 2, 1, then the trace is going to be one loop if you're in the Temperley-Lieb six strands. So you use them all. And it's good to know that. And knowing that, plus the Temperley-Lieb identities and cyclic permutation, because this says that the trace is invariant under cyclic permutation of the product, lets you find the trace algebraically. I give you an example, and you can enjoy yourself doing other examples. So here's an example like the one I had on the previous slide, whose trace is surely delta squared, because we know by drawing the closure that it's going to have two loops. On the other hand, if we had just confronted it as an algebraic entity like this one, this is the algebraic normal form for this. It's U4, U3, U2, U1, I'm sorry, 3, 2, 1, and 5, 4, 3, 2. And we're allowed to do cyclic reordering. So I'll just write sequences of numbers here, meaning the UIs. So we had 4, 3, 2, 1, 5, 4, 3, 2, and I do a cyclic reordering, putting the 2 out here. But now the 2 commutes with the 4, and so I get 2, 3, 2 in here. But 2, 3, 2 is 2. Remember, U2, U3, U2 is U2. So I get 4, 2, 1, 5, 4, 3. And then the 4 commutes with 2 and 1, and we get 454, and 454 is 4. So I get 2143, and that's the same as 4321 by cyclic reorder. But 4321 in TL5 is recognizable as having two loops. That's a standard thing, 4321, and separated from the remaining last line because we're in TL5, and that tells us we have two loops. So algebraically, you can determine the trace by using cyclic reordering and the temporally Lieb elements. And that, of course, is where it started with von Jones. He defined...
I was too late.
I'm sorry?
Before Kauffman came to talk about his lecture.
I didn't understand the question.
He doesn't have anything with Rashi and the lady.
I'm sorry, it's the sound. It's the sound. Is there a question? Was there a question?
I'm waiting for this.
I think Carmen is talking to somebody else in her room.
Oh, okay. If you're holding a conversation, please kill your mic. Yeah. Okay. So now you can have a nice time doing a comparison, because if you were to look, for example, at index for subfactors by von Jones, you'd see that he does everything in pure algebra with no particular interpretation of the algebra. And yet here in the connection structure algebra, you see how that algebra fits everything that goes on in the abstract algebra. So that's a further comment I wanted to make. And now, last time we were talking about quantum theory, and I just wanted to point out to you that now if you look at the notes in the Dropbox, you will find a version of what I spoke about last time in handwritten notes in there. And let me just take a few minutes and review it just so you see it again. This quantum theory in a nutshell is as follows: that a state of a physical system is represented by a unit vector psi in a Hilbert space. If the Hilbert space is finite dimensional, which is the way we're usually thinking about it for this purpose, then psi will be some complex linear combination of basis vectors, and the sum of the absolute squares of the coefficients is equal to 1. And the postulate in quantum mechanics is that the probability of measuring EI from the state psi is absolute CI squared, so that the set of numbers absolute CI squared is a probability distribution, but the set of numbers ZI is not. The set of numbers ZI, their values are called the probability amplitudes for these observations. And I say observing EI because it is assumed that there is either a thought experiment or a real experiment where the outcomes of the experiment are in one-to-one correspondence with the orthonormal basis states for the Hilbert space. And I didn't write orthonormal on this slide, but I'm writing it on the next slide somewhere. So the EIs are orthonormal, perpendicular to one another of unit length. And then the Dirac notation says that the dual vector, the covector, psi, I'll still say psi, ket psi, bra psi, this is bra psi, is the sum of the conjugates, of course, times the EIs. And then you see if you apply one to the other, you get the sum of the absolute I squared. The Dirac notation is convenient. And then finally, to complete the model, this abstract model, a physical process is a unitary transformation of the Hilbert space to itself. That means that the complex conjugate transpose matrix is equal to the inverse. And what that means is that the length of the vector is preserved under unitary transformation. If you apply U to psi, you will get a vector which has the same length as psi. And that means that, that this set of numbers is, again, a probability amplitude distribution, or a probability distribution if you take the absolute squares. And that is all of quantum theory except for the physics. In order to have the physics, you need to know more about the unitary transformation. That will come, we may come back to that. I wanted to give you an example, though. This is going beyond what I said last week. This is a nice example to have in your pocket. I'm going to have two little quantum elements here. One is an ordinary mirror at the bottom of the slide. Oh, and I have two states, spin up and spin down. And the mirror, when it reflects a spin up, turns it into a spin down, the ordinary mirror. And when it reflects a spin down, it turns it into a spin up. And that's it. That's its action. And if you think of the matrix of that with respect to this basis for the Hilbert space, two-dimensional, well, that's just an anti-diagonal matrix 1, 1. And it's its own inverse, and it's certainly unitary. So M has a unitary transformation associated with it. H is a little more complicated. It's a half-silvered mirror, which means that something comes in and it might reflect or it might transmit. And now this is a quantum mirror, so that means that the output of this is in superposition. When you apply H to an input, which is spin up, it becomes a linear superposition of spin up and spin down. And you'll notice that this is a unit vector in our space, since 1 over the square root of 2 on each component will give me a unit vector. And if I apply it to spin down, it has a different behavior. It's spin up minus spin down. And in particular, in terms of the reflection properties, spin up reflects to spin down, and spin up transmits to spin up. But for spin down transmits to minus spin down, a phase change, but it reflects to spin up. And those are my rules for this. H is called the half-silvered mirror. It's also called the Hadamard matrix by the people who use it. And so we have two quantum matrices here. You can check that this H that I defined is unitary as well. And you'll notice that without the minus sign, it would be singular, so it certainly wouldn't be unitary. Now, these are the components of a device that I can now make as a thought experiment. Here's my device. This is my device. This is the Mach-Zehnder interferometer. And what happens here is that a particle comes in, and then you can think of its different possible paths. It comes in, it gets reflected, then it gets reflected again, then it might get transmitted, or it might reflect, and reflect. And similarly, it may get transmitted and reflected and transmitted. That means there are 4 outcomes here, which I probably said all of them. And we can watch what happens as we go through each of these possible pathways, if we think in terms of the particle bouncing around in this little device. And I've indicated what the Hadamard does in each case. On the other hand, here's the Hadamard matrix, and here's the ordinary mirror matrix. And this device is representing the quantum process. First do H, then do M, and then do H. That's what happened. First you did H, then you did M, and then you did H. So if we watch the paths, we see that, for example, when we look at these two output paths, they're both up. And so they're reinforcing each other. If we look at these two output paths, one is down, they're both up is right with plus signs. And when we look at these two output paths, they're both down, but one is minus the other. And that connotes the destructive interference that happens here. Nothing is coming in, nothing will be seen. Similarly, when you put in a downspin, nothing will be seen here, but we will see, well, if we could see the minus sign, which we can't, but we see in the mathematics -2 times the downspin. But if you look at the matrices, you see that if you take HMH, you get 1, 0, 0, -1. And that indicates that the composite process, HMH, from the matrix point of view, is always going to be spin up if spin up came in, and always going to be spin down if spin down came in. The minus sign is a phase and is not seen by the probability, but you see how the minus sign is very important for what happened in the quantum interference. And you also see that by summing over all the paths that the particle takes as it goes through the system and keeping track of the phases, we get the same result as multiplying the matrices. And this is called the Feynman path integral in its most general form, but in this case, it is just the properties of matrix multiplication, because when you multiply matrices, you sum over all the intermediate possibilities for the indices of the matrices, and that's what's reflected in the path structure in this little device. So this little device is very good for doing quantum thought experiments and seeing how things work. You can go all the way to getting numerical results from it, and you can try different things. For example, you could put different phases in the mirror system, and you can ask philosophical questions as well. And I recommend a paper, which maybe I should put in the Dropbox, by Elitzur and Weidmann, who did some very beautiful thought experiments using just this much mathematics and the Mach-Zehnder interferometer, showing how to detect certain things without ever looking at them. They were showing how to detect whether a bomb was going to explode or not. But it's a nice thought experiment, even though it's a little violent. Then the further thing that I said last time was that Xian Yang was concerned with two dimensions of space-time, one dimension of space, one dimension of time, two particles, A and B, interacting and ending up in C and D like this. So that the Hilbert space here is the set of particle states, which are two spins, A and B, and the process of going from AB to CD is some unitary transformation for him defined on that little Hilbert space, so that R of AB is a certain sum of other states like that. And these coefficients, that's the Yang-Baxter matrix. For him, it would be unitary. I think we can use a full view. So what Yang wanted was that the amplitudes, and that's what these matrix coefficients are, they're the amplitudes, and for him they would be complex numbers. Those amplitudes should be only dependent on the permutation in the underlying braiding, although there's no braid group here. So here you see a permutation that takes A to F, B to E, and C to D on both sides of the ledger, and he wants the amplitudes to be only dependent on the permutation and not on the specific order of interactions. And that becomes the Yang-Baxter equation, and you want to write down what is this amplitude? What is this amplitude that you're getting? And so just in Bayer, here it is. You see, you can think of this as running over all the different possible paths, if you like. I start at A, and I might end up at K, and then I end up at F. But the B also ends up at I, and I have to run through all the intermediate possibilities, I, J, and K. So the amplitude is the same as the tensor diagram, tensor network multiplication of these matrices. That is, you simply write down each matrix that corresponds to, I want to point, this corresponds to that matrix, this corresponds to the JFKC matrix, and this corresponds to this matrix. And you write down each matrix and sum over all the intermediate index possibilities. Summing over all the intermediate possibilities is the same as summing over all the paths. It's also the product of the matrices. On the other hand, you can view it as a composite, R tensor I tensor R, and R tensor I. And if you look at it that way, then you can go ahead and compute. R tensor I applied to ABC is the sum of Rij, IJC. You didn't use C. Now that's a scalar, and I get it out of the way, and I do I tensor R, which means that I take on JC and sum over the indices KL. And then I take R again, and now I'm picking up I and K, and I and K, and summing over M and N, and I get this sum of repeated indices on I and J and K coefficient, which takes me from ABC to MNL. I changed letters. And that's the same as the Yang-Baxter left expression for the Yang-Baxter. And the right expression is similar, and the equality of the two is the Yang-Baxter equation. So in the formulation of quantum invariants, we don't demand that R be unitary, but it should be invertible. And we include creations and annihilations in their matrices. And of course, the Yang-Baxter equation becomes the third Reidemeister move. And it would have. I'll fix it later. That's a nicely woven crossing. It should have been this way. And other topological relations, which we've discussed elsewhere in these notes. So one last comment here. In this quantum framework, the not invariant becomes a vacuum amplitude for a process in the space-time shape of the knot, because you're starting in the vacuum, and then the particles are created and they wind around one another, do whatever they do using the R matrices, and then they get annihilated again. So you're computing a vacuum amplitude. And in the category framework, the Morse diagram for the knot is a morphism in the tangle category. In this case, a morphism from the base object back to the base object, and measured by a functor to a module category. And all of that way of talking, in fact, parallels the question of formulating quantum amplitudes as Yang did exactly. So that's a quick review of where I was then. And then we talked 2 weeks ago about the Morse diagrams. So let me just remind you what happened there. From the point of view of the sort of thing I was just writing, we have the creation and annihilation cups and caps. If you had the simplest example, then you would have the sum over M upper AB and M lower AB, and that would be the value of the loop. You need to have that maxima and minima cancel one another, and so the M matrices, upper and lower, have to be inverses of one another. And you end up with a translation between the moves in the Morse category, tangle category, and identities about the matrices. The M's are inverses of one another, the R's are inverses of one another, the Yang-Baxter equation happens, and there is a swing move between M and R bar and R and M that looks like this. And then you can write down examples of that. And the simplest example is gets us the bracket polynomial. So this is a nice example to think about again. I'll just slow down a little bit and go through the example, and then we'll do another one. In this example, I take the M to be equal to this matrix, IA minus IA inverse. And you can check that this M is equal to its own inverse. That is, if you square it, you get the identity. And you can also check that the sum of the squares of the entries of it, which should be the loop value, is the right one, right? Take the sum of the squares of the entries of that matrix and you get minus A squared and minus A to the minus 2. And then the R is A times a cup and a cap, and that's the M's, plus A inverse times lines which go vertically, and those are the deltas. And similarly for the R inverse. And these, which we can write out, this matrix, which we can write out, is in fact a solution to the Yang-Baxter equation, non-trivial Yang-Baxter solution. Here it's written out. So the R is A times M upper, M lower, and A inverse times identity. And so I'm interested in this guy here, which is a little temporally Lieb representer, this U. So U upper AB lower CD is M upper AB lower M, M lower CD. And so the U, if you display it all out, and here I've displayed it, I'm using two indices, 0 and 1. And they run 0, 0, 0, 1, 1, 0, 1, 1. I've chosen that order and that here. And then I put in the corresponding matrix entry. So the 0, 0 entry of M is 0. So the border is entirely 0. But here I have 0, 1, 0, 1, and that's this entry squared. And here I have 0, 1, 0, 1, and 1, 0, and that's the product of these two, which is 1. It is, isn't it? And similarly here, this is 1, 0 squared, which is minus a squared, minus a to the minus 2. This little matrix certainly has the property that u squared is delta u, where delta is our loop value for the bracket. So this matrix is interesting in its own right. It's a core matrix for constructing a representation of the temporally Lieb algebra. If you wanted to construct other UIs, then you tensor it with identity matrices and get this core piece in the right place. So for example, if it was U2, then you would have a line and then you would have a cup and a cap in TL3, for example, and that would be the identity tensored with this U. And now our matrix, the one that we want for the bracket, is A times that, 8 times U, plus A inverse times the identity. And that identity is this identity, 1's down the diagonal here. And so we take A inverse times 1's down the diagonal and add it in. And you will notice that A times this gives me, in this point here, a minus A inverse. And A times this gives me a plus A inverse, so this is 0 here, and you can check the others. There is, in fact, a solution to the Yang-Baxter equation. You can verify that directly if you wish. And it's convenient. I'm repeating myself, I know, but I wanted to go a little farther with this model, and I thought better to repeat it. So if you factor out an A from this, then it becomes a little more symmetric. This will still be a solution to the Yang-Baxter equation in the box. And now it has an a to the minus 2 here, and a minus a squared minus plus a to the minus 2, and the 1s and 0s. So if I replace the a to the minus 2 by q, then this would be q minus q inverse, and this would be q, and this would be q. And you see that I can describe it as q minus q inverse occurs when this index is less than this index, 0 is less than 1. And these two are equal, 0 on the top and 0 on the bottom, 1 on the top and 1 on the bottom, and these are equal. So this is a glyph that says, I want my indices to have that pattern. And this is the case where all indices are equal. That's where you got a Q, all 0 or all 1. And otherwise, there's a 1 when they cross over. 1, 0 crosses over to 0, 1. Now, I've described this in the case of two indices, but it is a remarkable fact that if you just take any ordered index set, whatever, then you have a solution to the Yang-Baxter equation. Any ordering at all, as long as you have a monotonic ordering. So there's a larger collection of solutions to the Yang-Baxter equation. And if you want to get a feeling for checking that something is a solution to the Yang-Baxter equation, you can take it as an exercise to prove that these all satisfy it. So now let's look at it a little bit. I'm not going to go through the details of checking that it satisfies the Yang-Baxter equation, but look at its formal properties. Here's R row, and here's row inverse. The Q got reversed, and the inequality got reversed. So if you take R row minus row inverse, you get Q minus Q inverse times less, greater, and equal. See, less, greater, and equal. And this part drops out because it has the same coefficient. But less, greater, and equal as an index requirement between two parallel lines is just two arbitrary parallel lines. They are index-wise equal top and bottom, and they may be less than each other, greater than each other, or equal. So that's the identity. So this represents the identity, and we have that rho minus rho inverse is Q minus Q inverse I, and that corresponds to the Skene relation, and it shows that rho satisfies the Hecke algebra identity as a matrix. So let's go a little further. I can define an oriented state sum in the following way. I'm going to do just what I did with the bracket. I'm going to expand a crossing, but now it's an oriented crossing. And I expand it into a local glyph saying less, plus Q times a local glyph saying equal, plus a crossover glyph saying not equal. And then the states of the diagram consist in replacements of crossings by these little glyphs. So you smooth in an oriented way at every stage except one where you cross over. The two basic ways of changing the crossing are to smooth it in the oriented way or to put it down as a crossover. But it's put down as a crossover with an indicator that they're not equal if it's a crossover, and if they smooth, that it's equal or less than. And then you have a diagram like this diagram, a nice simple example here. You have a diagram with some logical indicators on it. And then you get to label the loops in the diagram from some index set. If you were going to reproduce the bracket, you would label from two indices. But if you were going to reproduce some other invariant, hopefully, then you can label from whatever indices you want. So you take an ordered index set at the outset, maybe from 1 to 100. And then you get to label this state. It becomes a labeled state, and you get to label it with labels like 1 and 7. That's okay, because the less than sign says that this must be less than that. So then it becomes, let's use a term that was introduced by Vero many years later. We'll call it an enhanced state when it has the labels on it. So the bare state is this logical structure, but when it has specific labels on it, like 1 and 7, then it's an enhanced state. And this enhanced state, there are many of them. If I had 100 labels, then I would choose distinct pairs from 100, and there are a lot of those. On the other hand, if I tried to label this one 100 and that one 1, it's not allowed, so it just doesn't occur at all. And then I'm telling you on this slide how you evaluate just a bare circle in this model. In the bare circle, you sum over all labels, so that's I and D is the index set. You sum over all labels, lambda, some lambda, which we haven't determined yet, raised to the minus a, because I regard this as having a rotation number -1. And this one to the plus a, because I regard this as having a rotation number +1. So you keep track of the rotation number of the circle. That's because everything is oriented. So here, if you evaluate it, you sum again with the individual evaluations, but you're only allowed to sum over the ones that are allowed. So this would be the sum over indices a less than b, lambda to the a, lambda to the minus b. So now you know how to evaluate such a state sum as a graph invariant, right? You expand it into states, and then you evaluate each state, which is a collection of loops, by this method, and you have a state sum. And then it is possible to adjust this so that it's an invariant of knots and links, and you can get the Hompley polynomial from it. I'll give you a detail in the next slide. I also want to mention a problem which has been attempted by many people, but probably not successfully yet. And that is this: if you happen to like covariant homology and you think of it as coming from the bracket states, then you could have the feeling that you could produce Kauffman homology by using these states. I mean, a generalization of Kauffman homology by using this combinatorics to underline the categorification. That's a remark for the future, but it hasn't happened successfully yet to my knowledge. So as I said, the lambda will be determined later, and the value of a collection of loops is what I said. For each loop, you take lambda to the rotation of the loop times the index on that loop, and you take the product of the lambdas. And that defines a state sum. For example, here's the evaluation of a little curl. I expand it here with a less than sign and an equal sign. And there is no crossover, because crossover not equal is logically impossible. You can't color a line not equal to itself. So we get Q minus Q inverse times the evaluation of that plus Q times the evaluation of that. Now, what's the evaluation of this? You can have A in here and B in here, and they have to be less than one another. And this is a negative rotation, so I get lambda to the A minus B. And then this would be labeled A. In this sum, I get the same label, A, and A is equal to B. Oh, and I kept writing it in this pedantic way. I didn't write the difference correctly. Oh, I see. I actually made an algebra error. Excuse me. There should be no A. I'll fix it when I put it in the Dropbox. I meant, of course, the value of this one, which is lambda to the minus B. And there is no A here because I'm not picking up anything from this. This is abstract. So it should be lambda to the minus B. Easy to make an error. And then you can collect this together. And you would like this to be simple. So you have to do some work to see how to adjust the model, but you get the picture now. And then here's the way it works. If you take your index set to run from minus n to n, and you take lambda equal to q, then you can verify that everything does indeed work. And the model gives you the regular isotopy version of the Humphrey polynomial. That is, it satisfies these rules, which means that you would have to normalize it by multiplying by an appropriate power of this to get the usual Humphrey polynomial. This state sum, like the bracket, will be invariant under the second and third Reidemeister moves and behaves this way under the first Reidemeister move. It's very nice. You get an infinite family of models that give you specializations of the Humphrey polynomial, and it runs over all the integers, all the natural numbers. And so, in fact, a little algebra checks for you that you have proof that the Humphrey polynomial exists. So you can compare this with Markov trace Heck algebra approach. It's really very close to it. And it's a very nice model. I'll have some more to say about it, but let's go on.
Is there another problem with you've got two right-handed crossings at the bottom there?
Thank you. I'll fix that.
Yeah.
Good. Here is another kind of model that is interesting to think about. It's a piecewise linear state sum model. And this model was abstracted from statistical mechanics by Vaughan Jones. The one I'm giving in the piecewise linear form adds piecewise linear to it. But if you look at his specific journal paper on statistical mechanics models and knots, you'll see he does it using curves rather than piecewise linear, and integrates along the curves to do some of the rotations. It's similar. The piecewise linear model actually occurs in some statistical mechanics papers by Perk and Wu. So what we're going to do now is we're going to have an angle, because it's a PL diagram of the knot. And so at a given crossing, we're going to associate to it an R, like we did before, an ordinary R matrix, Yang-Baxter matrix, and then a lambda to something that measures the angular turn, and in relation to the labels, the spins coming through, D minus A, as you see. And we're going to assume that the spin is preserved. It's a way of remembering this condition on the R matrix. We're going to assume that the R matrix doesn't work unless A plus B equals C plus D. It's zero otherwise. So the fact of the matter is that the physicists' scattering matrices had angular dependence, where the angle meant something to them, as well as internal dependence on the spins. And so this is a little more like the physics, but the physicists, of course, noticed, Perkin Wu noticed that they could think of those angles in terms of angles between the lines if they wanted to. So we're going to do that. We're going to use this, and of course in the inverse matrix we invert this matrix and we leave the angular part alone. And then there's a further kind of angle that occurs in your diagram, and that is it goes along with piecewise linear and then it changes direction. And you calculate the angle for the change of direction, and you associate to that another bit from that variable lambda, theta times the index. And we are no longer in a Morse diagram. So you just have a piecewise linear diagram, and you have some angles that happen, and you have these R's which you look at and pick off their scattering data. This, of course, is what corresponds to the cups and the caps. This is what happened to them. And if you want, you can try to think about how you would translate this model back into one involving only cups and caps. If you drew the model in a rectilinear way, then you would see what to do. Then all the angles would be 90 degrees. You can work with it. So then the model is the sum of the products of the weights, just as before. So you have the angular weights, you have the crossing vertex weights, two types of vertex weights, order 2 vertices and their weights, order 4 vertices and their weights. You take the sum of the products of all of them over all spin assignments to the diagram, and you get a partition function. And then you get a certain condition that has to be satisfied in order for it to be an invariant of regular isotopy. It's interesting to work through the details. You can find the details for this PL model in my book, Knots in Physics. And you can compare this condition with the one that we didn't mention. We mentioned it, I think we mentioned it long ago, back here, oops, when we were talking about oriented models. Oh, didn't we talk about oriented models? Ha! I thought we did. Oh, I'm talking about oriented models after this model. That's right. Okay. Yeah. Never mind. So some fun occurs in the, so I'm saying that you get a theorem. I lost it. There's the theorem. You get a theorem about this model that tells you that it will be invariant if the R matrices satisfy a certain condition in relation to the lambda. And this very condition will come from just looking at Morse diagrams and oriented models as well. There's the piecewise linear Reidemeister moves, if you were wondering. And here's the sort of geometry that you have to think about when you're doing the details of this model. I don't care to go into the details. But I do want to point out this. If you ever look at physics literature about the Yang-Baxter equation, this angles picture it shows you that because of the way the exterior angle of a triangle is equal to the sum of the interior angles, that the Yang-Baxter equation for what we wrote down becomes the usual one, then the sum of the angles, and then another angle. So each one has an angle associated with it, theta, theta prime, and this angle is theta plus theta prime. So you see you have this angular condition with the sum of the angles in the middle. And that in fact is the form of the Yang-Baxter equation that happens in the physics. They had an extra parameter, and their parameter changes as you go from one thing to the next thing to the next thing.
Yeah. A lot of bugs. How was the backyard?
Pardon me?
All right.
Random noise.
Oh, that's really cool. All right, but right now, hey, you, come here. Find a bike club right
Oh,
now
sure.
and
Could
find
you
out when
mute
they're next
everybody
meeting
else?
it. You don't have to go to every single one of them.
What's the comment?
That's fine. You have work, but you don't work
Joe's
every
talking to
weekend.
one of her children.
You don't work every day.
Perhaps you could mute people.
Yeah, you know, you have the opportunity to discuss by using the typing in the chat line, right? I appreciate comments if they're directed at me, to me. Anyway, that's the full looks of the Yang-Baxter equation, but of course the interpretation is not that it's an angle between lines. That's due to Perk and Wu, I think. I'll check the reference for you. Yeah, that's my remark. And I'll skip this remark. You can read it. The angles can be thought about in terms of relativity, but I don't want to go into that. So having given this much information about the statistical and quantum statistical background to the link invariance, you can ask lots of questions. Many questions might occur to you, like, why does he misspell the word question? It is to be hoped that this physical background will help shed light on the nature of the invariants and also on their link homological generalizations that we'll discuss later. I hope so. I think that that some of these models should reappear in not just the bracket model, in thinking about categorified link invariance. Now we get to Edward Witten. And in 1988, 1989, he gave a quantum field theoretic interpretation of the bracket state sum and its generalizations, and he due to Jones and Rashetikin and Turayev, and he used functional integration. He used a generalization of the Feynman integral. And I want to make a historical comment, which I have put in this slideshow in a little bit the wrong order. So let me find it. Yes, there it is. We're back in 1986 now. I was telling you that Witten did that breakthrough in 1988. But on October 3rd, 1986, I received a letter from Vaughan Jones, and we were just beginning to have these kind of state sum models that I just showed you emerge, that generalized bracket and used solutions to the Yang-Baxter equation. And in the letter, he outlined how to do that in the Homfley case, specialized Homfley. And then at the end of the letter, he wrote the following. He said, the model is very suggestive, meaning these state sums, as to the real meaning of the polynomials. L should be replaced by a link in 3 space, meaning an embedded link in 3 space, and the states by functions from L to an n+1 dimensional Hilbert space, perhaps distributions or something. I can't read that line. And the sum over contributory states by an integral with respect to some Wiener measure of an interaction term depending on the link in R3. Thus, it is an object of gauge quantum field theory on L. The gauge group is, in this case, SUN+1. That's the kind of model we were just talking about. I'm morally sure that if one replaces the gauge group by SO2n+1L+1, we'll obtain Kauffman polynomial. And there should be other polynomials for all the Coxeter-Dinkin diagrams. PL of n being the AN series, thus the two variable polynomial is the kind of generating function for the AN series, and the Kauffman is the same for the BN series. The ubiquity of the original Jones polynomial is explained by the fact that it corresponds to SU2, which is of course everywhere dense in this stuff. And of course, all that is correct at the level of doing state sums and at the level of the quantum groups. And I think he was at that point already aware of Drinfeld's work and the quantum groups and the proliferation of solutions to the Yang-Baxter equation, but he certainly was not aware of a solution to the gauge quantum field theory idea of doing an integral. But he has, with great prescience, put his finger on the essence of what happened later with Witten. So it was very interesting to find the letter and reread it and see that he had said that. I thought I'd show you that. So I want to tell you about Witten, but I think we're nearly out of time. And so maybe this is a good point to stop, and we'll go into Witten next week.
So are there any questions?
Could you go to the box, temporarily leave pictures one more time?
Yeah. Mm-hmm.
I'm afraid that you've shown this maybe 2 or 3 times, and maybe a bit earlier.
Oh, yeah, but you're talking about this business here, right?
Yeah, exactly.
Yeah, well, that's an example, but maybe there's a clear. Here's a nice clear example.
Okay. If I look where the vertical lines are, I reckon that I'm reading 3, 2, 4, etc. And I don't see that in the
Sometimes, sorry, it's my own habits. I label the lines 1, 2, 3, 4, 5, 6, 7 usually, but sometimes I label the spaces, in which case this is space 1 because it corresponds to U1, and this is space 2, and this is space 6.
Right.
Let's suppose that you're used to labeling lines. Then the 3, 4 combined with a cup below. Maybe you want one where I've translated everything into both forms, like this. Yes, let's use this one. Here I labeled the spaces, but here we have 1, 2, 3, 4, right?
Mm-hmm. There's still one that's
I made a mistake. That's right.
There's one that's a bit earlier where I almost.
I see what I did. I have to fix that too. I was doing my friendly labeling of spaces. No, I wasn't. I was labeling the lines here, but I labeled them on their left side. So read it correctly. It's lines labeled, not spaces labeled. This is a U4.
Okay.
All right. It's just indexing.
Yeah.
Right. What U is this? This is a U4.
Okay.
All right. 1, 2, 3, 4. U4. Okay. So this is U4, U3, U2, U1. This is U5, U4, U3, U2. And this is U8, U7, U6.
Okay. Thank you.
Yeah. Right. That was all. Yeah, I wasn't being very consistent about the labeling. Other questions about it? No questions.
I was wondering if CERN had yet discovered this new fundamental particle, the quasiton.
I'm sorry?
I'm just making a joke.
Yeah, that's all right, but I didn't hear it.
Quasiton.
It's just, The
We wondered if
quasi-tone?
CERN had found this quasiton. It's a good fundamental particle.
There are lots of questions about it.
Yeah.
Other questions?
So, yeah, just, I can't state this correctly, but if you can put that angle parameter into the Zamolodchikov equation, then you solve a major problem in statistical mechanics. So if you can find a solution to the Zamolodchikov equation with such an angle parameter, Vaughn was telling me that this is a highly important problem.
Is that right?
Yeah.
Just for the equation itself to have an analogous angle parameter?
And solution.
Of course, you solve a model in that higher dimension to actually exactly solve it. That would solve a major statistical mechanics problem.
Yeah.
Or maybe that's what you mean, right?
Exactly.
Right. If we take these models, which are two-dimensional, and put them up into 3 dimensions in the statistical mechanics way, then no one has really done what Onsager did. No one has fully solved these models, even the Ising model.
Okay.
And as you see, one last comment. As you see, there's a really strong connection with combinatorics and graph theory going on here under the hood, which I'm kind of ignoring except for the surface structure.
It's amazing, all these connections.
Yeah.
Okay, well, if there are no more questions, I'll stop recording.